When I was reviewing the recorded lecture, I just noticed that we discussed the time series decomposition model, and we successfully forecasted the value, but our objective was basically to estimate the forecast value for quarter one 2019, right? And you see there is no forecast value right here. So if you extend the trend value right here, so, and then the forecast value right there. So the forecast value for quarter one 2019 is about 87.6963. So if I plot them all of these values together and we compare the actual with the forecast line, so it's something like this. I'll just remove all of the rest of the data. So here you go. That is the projection which we were talking about, right? So the blue line represents the actual line, the actual values, and the gray represents the forecasted value. And here you go. This is your forecast line projection that in quarter one 2019, the value should peak around this following the pattern of seasonality. So that's about that. That was the time series decomposition model. Furthermore, we estimated the forecast error in this particular model, and this 8.61 represents that if we use this forecast model, then we'll get on average 8.6% error in our forecast. Now, to sum up the forecasting models, we started with the naive model, and naive is the basic forecast model in which we simply see that whatever is the previous actual value is the forecast value. So for instance, if I tell you that what should be the next Friday's sales value, so if you are working with the naive forecast model, you will say that whatever is the previous Friday's sales value. So it's simply this. So that one, we started with a naive model. Majority of the businesses, they use naive model without even knowing that they are using naive model. It's the most common form of forecast models, but when the complexity of a particular business increases, the naive model, its failure, it's felt significantly. Then we move towards mean. So what was mean? Mean was simply equal to sigma I is equal to 1 and n, whatever is the number of observation divided by n. And we talked about that where we can use the mean value. Mean value can be used in a case where the standard deviation value is significantly less. So this means that the data, the values, the data points are close to each other, and there are no significant smaller or bigger values in a data set. In that sense, we can use mean. Then we move towards the moving average. So if you think about the generic form of a moving average, it was something like this. So we consider number of lags, and moving average depends on what we call the value of n. So n is basically the number of lags which we use. So first lag is a subscript t minus 1, then a subscript t minus 2, then a subscript t minus 3, and so on and so forth, dot, 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 a subscript t minus n, and divided by n. Once again, I'll represent something like this. So if I explain this bit, so it should simply mean something like this: x1 plus x2 plus x3 up till xn and divided by n. And we talked about that the biggest flaw in mean is something like this. So if I write a variable x, its coefficient is 1. So no matter what value is x1, we give it a weight of 1. Whatever is the value of x2, we give it a weight of 1, and so on and so forth. And if we keep doing this, this manner of weighting observation, then we basically introduce bias in a data if the data set has both small and bigger values. And once again, I explained this value of n. What's this value of n in mean? discussing with reference to the forecasting models, that is simply the addition of all the weights assigned to each observation. Moving average also performs the same thing. Uh, but since it's moving, this means that the average estimated through moving average is dynamic. It changes with time, it skips the previous value, and it is more concerned about the most recent value. That is one significant upgradation in a mean. Where can we use moving average? Moving average are supposedly in your both books, Hazer et al. And William Stevenson's. They recommended that moving average should be used in a case where the data exhibits none to weak trend in data. Similarly, if we talk about the next model, that is a weighted moving average. The weighted moving average is almost the same, but here the weighting factor is added. So weighted moving average also depends upon the value of n, number of lags, but it represents lags, but also what we call weights. What does that mean? So if we say that we are supposed to apply what we call three period weighted moving average, then this means 3n, so there are 3 lags, so a subscript t minus 1 plus a subscript t minus 2 plus a subscript t minus 3. We got 3 lags, and similarly we got 3 weights, so 3, 2, 1. We are supposed to write that in a descending order. So the first lag always gets the highest, then the second weight goes to the second lag, and the last lag always gets the lowest of weights. And then we are supposed to divide that by the addition of all weights. So 3 plus 2 plus 5, and that is a 6. And that is how weighted moving average estimates a forecast value. So there are two factors involved right there. One is the moving part, and another one is basically the weighting part. About that weighting, I also explained that the total sum of weight is 6. So if I divide that by 6, if I divide that by 6, and if I divide that by 6, and I add them all up, if I add them all up, the value is equal to 1 or 100%. So remember that the sum of the fraction of all the weight should be equal to 1 or 100%. If that's the case, then the weighting is done correctly. This gives us a slight flexibility as well. So for instance, instead of writing 2, 3, or 1, what if instead of that, we assign weight something like this? We give about a 70% weight to the first observation. So when 70% is given to the first lag, how much weight is left? The whole weight should be equal to 100%. So 30% is left. Let's suppose 20% of the weight is assigned to the second lag. So how much weight is left? The 10% remaining is assigned to the last lag. In that sense, if you think about that, 0.7 plus 0.2 plus 0.1, that is equal to 100%. So now instead of 6, we are not supposed to divide it by anything. We are supposed to divide it by 1, and we don't do that. So that is the again the next weighting regime in weighted moving average. Where can we apply weighted moving average? Weighted moving average is always recommended in data sets which exhibit strong trend. When they have a strong trend, we tend to apply weighted moving average. Then we move on towards the exponential smoothing. Exponential smoothing can be applied on both type of data, depending on the value of alpha. And the range of alpha is between 5% and 100%, 5% and 75%. So if a data has a strong trend, we take a value close to 75%. And if a data has a weak to no trend, then we take a value of alpha close to 5%. And how to select this alpha value with the incremental increase or decrease? We discussed that thing back for your reference. It's what we discussed in model selection procedure during exponential smoothing. So exponential smoothing in that regard can be used for both data types, with a strong trend or with a weak trend. Now, moving on, when we started discussing a trend adjusted exponential smoothing, that is a remedy for one of the problems which we face in exponential smoothing, and specifically in an exponential smoothing with the strong trend data, when the alpha value is close to 75%, usually we notice the some evidence of error bias. And what's the error bias? Error bias is basically the consistent either positive or negative error, and we discussed that in quite detail. So in order to mitigate that particular problem from exponential smoothing, we basically adjust this exponential smoothing for trend. So trend adjusted exponential smoothing is primarily used in a data that exhibits strong trend. And lastly, in the previous video, we discussed what we called a time series decomposition model. And time series decomposition model is used in a condition in which the data has more than one component. So for example, a weak trend previously, in the previous video, the data set has had a weak trend with a strong seasonality, or a strong seasonality and a strong trend, or a weak seasonality with a strong trend. So in such cases where the data components are more than one, then we switch to what we call a time series decomposition model. These were the models which we discussed in your forecasting module, and all of these models were basically a time series forecasting model.